methodology which is developed at Noesis by Corey. It is a it translates the semantically annotated sensor observations into high-level abstractions with the use of perception cycle. So it formalizes both background knowledge in the form of in the form of a bipartite graph as entities and qualities, and also it formalizes perception cycle for minimizing explanation.
What is the cycle?
Perception cycle?
Yeah.
Cycle in
Perception cycle.
perception cycle is this thing what we discussed.
Oh.
So this is being formalized by IntelliGo. So it is used in 3 domains, which is weather, rescue, and healthcare. In case of weather, it relies on weather sensor data from weather stations, and it comes to, with the use of perception cycle, it can come to useful conclusions like whether it's a blizzard or flurries, like that was telling. And it's the same case in rescue and in healthcare. It uses these two, both background knowledge and perception cycles. Yeah, so here also, this is the mobile MP app where perception cycle is used. Like it takes observations from the human, asking questions to the human, whether you're feeling lightheaded, or you're taking deep breaths, and such kind of question answering takes place where it will allow us to come to good conclusions and explanation as to what exactly might be the problem. So, Dr. Shah, like, this is the mobile MP which takes place, which we have developed in Noesis, right? So this is a link to the video taken by them.
Yeah, you can go, people can click on that. Why don't you click on this, see what comes up.
I just wanted to.
Oh, this is your busy, right? So
Yeah,
it's not showing.
but yeah.
Yeah, that one. Okay, so basically, in fact, just moments ago we had Professor Arthur Pickoff, who is, I think, Dean at School of Public Health here, and Professor Shalini Fortis. She's a pediatrician and treats asthma patients, so children with asthma. So they were there. Here, this is an application that we kind of have developed and now waiting for it to be tried with real patients, where your patient, there is a series of sensors, the weight, the heart rate monitor, blood pressure monitor, and it can, all these devices can talk to a mobile phone. On the mobile phone, you have an ontology for cardiology and IntelliGo based reasoning system. So all those sensor data come in, and the idea here is that these sensors can, patient may be asked to collect weight twice a day, let's say. The heart rate monitor is constantly updating, measuring heart rates, and the blood pressure maybe again a couple of times a day. Now, no doctor has the time to look at all that data. The idea is not to look at the data. Idea is to identify situations where a patient might be at risk. So let's say that patient, whether you just continue monitoring, risk level 1, whether you double check whether the patient has taken all the medications, risk level 2, whether patient's data should be sent to clinic and somebody should look at it, risk level 3, whether patient should go to outpatient or talk to clinician over the phone, whether patient should go to ER, risk level 5, let's say. So suppose, how do I convert all this low-level data into meaningful abstractions, right? And one of the very exciting things is that we have a paper that says semantic perceptions, converting observations into abstractions. So that paper that Corey has with us, with me and Professor Prasad, that's the most downloaded paper in 2012 from IEEE Internet Computing, where it was published. So, and today afternoon we are discussing similar application or similar situation technology for asthma, right? Anyway, so that is kind of application that is there. You guys can look at that. There's a video here. You can see how different data can be collected. Patient may click on this and sensor, and then it gives you ability to pick up the data from sensors, and then abstractions. This is at this level. I will show you that, and so on and so forth.
Professor?
Yes.
So let's say we have the data like very low level,
Hmm.
and then from that you get the abstraction. So I'm wondering, how do you represent numerical data in IDEA? Is it like
So how do you? I don't know how we are doing reasoning on that number, but you can certainly check the number is less than 90. That should not be a problem at all. But if you want to do arithmetic computation, then that is a problem. So we are not. You don't have to check. We don't have to add up two values, right? But if you say whether the number is less than 90, I don't think that's a problem at all.
Dr. Sheth, how important are the questions that are posed in this app to the end user? Is it just corroborative evidence, or do we factor in people putting in incorrect answers and things like that, or how critical is it for the app to function correctly?
Well, if there's a mistake, then you probably would take the patient to, you might show high level risk than in reality that is, as an example. That's the worst case, right? Because this is not automatically giving you medication advice per se. But that reminds me of one interesting thing this application does. You have there's a series of questions that you can be asked. But what happens is that if you ask too many questions, people don't like to, they will give up. In fact, many of these patients are elderly people, and you ask them 12 questions every time they, interact with the device. That's not going to work for them. So what we do is we ask them contextually relevant questions. We try to ask only the questions that are most relevant to them and only when necessary. So that is a very interesting aspect. Now we are not proven that this is working very well, but that's what we've done. And so instead of asking routinely these 12 questions, so there is a system called Vanda that people at UCLA have developed, but that kind of would ask all the questions or the same thing they would go through. Here we are asking contextually relevant questions and limited number of questions.
And that comes from the ontology based on what physical parameters the sensors are.
Right. I mean, if you see that there is a particular risk level, then that is the case. Or you say there is a patient has gained weight. Well, what else should we really need to know? If patient has gained weight, and if something else is there, if some symptom is there, then do something. In that, do you feel like your body is bloated or whatever? So in that case, you ask those questions. Otherwise, you won't ask the question. You may also ask questions to invalidate some hypothesis. All right? Do you have a lot to go?
His part, mine's done.
So, if your part is done, then I'm going to take a break and ask our guest here to, we'll take a detour here. Right? So, Thomas, Dr. Christopher Thomas. This is my first chance to say Thomas. Some of you know that he defended his PhD in December. He is waiting for his visa stuff to be done, and then he's going to join Samsung Research and work on a very, very cool project, but I can't tell you what that is. You can ask him directly and see if he can tell you. But he did something very interesting that is relevant to our exercise. So I want him to just kind of, this morning we were talking, he's possibly writing a book, and with some, I think, interesting conversation that I thought would be interesting to class, particularly in the context of your assignment. So one of the aspects of the assignment is that, you're talking about semantic search and how could you use knowledge to improve the search? That is one question, right? And it so happens that Topher's thesis was on knowledge acquisition. Okay? So over the period of time, there have been a number of approaches. I think the title of his thesis is knowledge acquisition on the web. There have been a number of approaches for creating knowledge, and his was a unique one. And I'll let him describe it, I'll chime in if I need to say something. But while I don't know whether he will describe anything unique about creation of Google knowledge base, but you know that, well, one of the things I wanted you to conjecture is how such knowledge base could improve the search. Well, let's just have a little detour and understand different ways people, different researchers have attempted to create different kinds of knowledge, right? So there it is, Christopher. Why don't you just watch here?
Dr. Topher.
It's been. You just wanted to say that?
Yes.
Okay. Good. I'd like to hear that. Many people say that. Well, in my dissertation, I discussed how knowledge could actually be acquired in a system like the web, and I make a distinction there between real knowledge and information that can be extracted. So, kind of give steps that can be executed to get from text to knowledge. So, knowledge is traditionally defined in epistemology as justified true belief, which means that it is not enough to have a piece of information, like triple, for example. It also needs to be true and justifiably true. So, a step to get a triple from a text is, for example, through information extraction techniques, and I believe you've talked about that in this class. The step to get to knowledge from there would be to have a justification procedure that says, oh, this extracted triple is actually correct. When you look at work that has been done in information extraction, you will see that a lot of the triples that are extracted are not really true, or they're meaningless. So when you let a computer simply use some NLP techniques and parse text, it will come up with things like, with triples like, he saw the light, something like that. Right? So who is he? We have no reference for that. Or it will say something like, 6 out of 10 countries signed the agreement. Again, we have no reference for 6 out of 10 countries. So even though the extraction was correct, it is meaningless. So you need usually a human to say this is correct. And in my dissertation, I discussed ways to do that maybe efficiently, and have thousands of people work on that without them actually knowing that they're working on it. So, for example, when you're using the Google Image Labeler, do you know that? Google Image Labeler example. It's a game with a purpose. Like, it lets 2 people play an image annotation game. It shows 2 players an image and says, hey, what's in that image? And the goal is to find the same word that somebody else found. There's a tree in an image. You say tree, and the other person says tree, and then Google says, okay, you get 10 points, move on to the next image. So, because it's 2 people saying the same thing, thing, there's some justification for there actually being a tree. The next iteration of the system, if you've ever played Taboo, you know that there are some words that are not allowed to use. So Google will cross out tree, and you have to type in oak tree, for example. Yeah, so while playing this game, you help Google get knowledge of things in that image. And something like that should also be done for the validation of information, of statements. You know? And in this lab, we did a browser project called Schooner. Is anybody who's worked on Schooner? Oh, yeah. Hi.
I gave a little demo of Schooner during one of the classes actually, so they've seen what it does.
Yeah. So in my dissertation, the hypothesis was that as domain experts in that case browse through triples that are given by the system to Schooner as guidance for browsing, it is more likely that people will browse correct statements than incorrect statements. And some preliminary analysis actually supports that hypothesis. But yeah, it is important for knowledge acquisition to have a validation step. In conceptual terms, the outcome of my dissertation, and have a technical part that has information extraction. Other than NLP techniques, my dissertation I use purely statistical, pattern-based techniques that don't rely on parsing of sentences. And the advantage of that was that these kinds of spurious triples, like 6 out of 10 countries signed the agreement, don't come up there. So pattern-based information extraction is more of a classification system. It classifies tuples of objects into relationships. So, for example, there's a relationship signed, or signs, and it says U.S. signs, U.S. comma start agreement. Signs Russia start agreement. We try to extract more of these than just reading a sentence where the computer does not actually know what's going on. Can you direct me more in the direction of this class? Questions I should answer?
I think if you were to kind of just review what we discussed in the morning, characteristics of something like Wikipedia, of Yago, of what user can generate, of
Okay.
Freebase and its extension that this is in the process, the kind of techniques different people use, and the 4 category of usage of this knowledge that we discussed. So just to question answer.
Okay.
And they are focusing on search, but they can get a feel of what happens.
So still get to go a step.
Can I ask one question
Yeah.
before I forget? So you said about verification of the proof
Mhm.
for this agreement statement. So did you really do that automatically, or just
Well,
say that is a problem?
We had limited data for the Schooner browsing, so I could not make a really informed judgment there. But the data that we had a couple hundred data points. They pointed in the direction that correct triples were browsed more often than incorrect ones. A lot more often, actually. But I have some hypotheses there too that say, oh, what if an incorrect triple is just very interesting that everybody would click that? Like, how would we identify that? You have a triple that says smoking is healthy, and you browse some medical database, you first of all, that would give you a higher justification, most definitely. Yeah? So there are two things though that you need to make sure. Is it correctly extracted, so just syntactically correctly extracted from all these places? Yeah? And then, yeah, if you can find the same statement correctly extracted 10 different places, it could, it's more likely to be correct. But I remember there was one thing, so what is it called? What was that RDF extractor called that then Microsoft bought? That company? Shed, do you remember that?
Sorry?
Like the company that Microsoft bought, the extraction? PowerSet, exactly. So when the Borat film came out, there was something Borat said that George Bush drink the blood of our enemies. Yeah? That was copied to many, many blogs on the internet. PowerSet extracted that and put up a triple. George Bush drinks blood. So there you have everything, right? You have multiple sources, you have correct extraction, but it's still wrong. So in the end, it is better to have a human somewhere. And the idea was also with this with this Schooner project, like when triples are browsed more often and thus get a higher confidence, would still more use that as a filter to then give the highest scoring ones to users. So let's say we have 1 million extracted statements. Yeah, we kind of have an idea that, well, 100,000 will be really correct, so we would give the users that we have only the top 100,000 rather than let them go through everything. So it's kind of take some work away from the users, that we don't have too much, only give them the ones that we kind of think are okay. And there could be other ways, like if we can, if we have a logics-based knowledge base, right, and we can really deduce something as well. It can be proven just by virtue of other statements that are correct in the knowledge base. Then you may not need it even there.
But your example about the blogs, in many blogs talk about the same fact, which is not true.
Yeah.
In the case of Schooner, you use the data from the netlines.
Yeah.
So that, I think they are more like trustable compared to the blog.
Yeah, yeah. So if you know your sources are already trustworthy, you would have a lot higher confidence. But yeah, it is a matter of your sources. If you know something about your sources, you can make a more informed decision even before asking the human to verify.
I have a question.
Yeah.
How did you prevent bias from entering into your, you said you limited what the users would see, like just in the
Mhm.
top 100 matches.
Yeah.
So you would limit that. How would you prevent bias from getting into there? Because you're physically cutting it off at a certain point. So
Yeah.
your
Well, I just
bias
said
is-
something arbitrary there with the top 100K, but
But did you like take into account biasing your data towards one way or another? Like how did you avoid doing that?
yeah, so it would, well, the bias would be towards, like, if I can go with my example of using Schooner to do that, the bias would be toward documents that are browsed or triples that are browsed more often anyways. Yeah? So, but that also means that's the triples that users find interesting to begin with, that they would use more often. So that may, at least in that case, be a good bias. And then maybe if the research focus of the users changes, they will move to other parts of the knowledge base, browse, have other triples that help them browse, and then make it up. So it is a bias, but it may be an okay bias to have.
So there's a way to check like if the bias is affecting your data one way or the other. So was there a
I-
score penalty
No,
function?
I did not look at that.
Okay.
But I think you have a valid point that maybe it should be normalized.
Mhm.
Like
That's what-
maybe
yeah,
on a log
normalized.
scale rather
Yeah.
than an absolute scale.
Mhm.
And things like that. semantic web is now, let's say, the name semantic web exists now since I guess 2001. The article came out, and even before that, people had been working on building knowledge bases, building ontologies. Knowledge bases are an old thing, an OpenAI thing, and up to Wikipedia, knowledge bases were usually built by experts, putting in pieces of knowledge that are relevant to a certain area, or there were some working groups that tried to build top-down ontologies to kind of provide an umbrella for other people who build ontologies so they can fit into these upper-level ontologies. Famous project there is called Sumo, standard upper standard upper ontology. What does it even stand for? I forgot. It's an IEEE project where they really try to define top-down. What is a thing? What can a thing be split into? Living things, artifacts, like top-down modeling, like that. The problem with all these things was that it was very sparse. We did not have much knowledge come out of that. We could make a small knowledge base for ourselves and then plug it into Sumo, for example. But there was no breadth of knowledge. And there was even Psych, the big Psych project going on, I think, since the 80s, as far as I know. Doug Leonard, a famous AI person, they tried to get a big knowledge base for common sense reasoning. Psych would contain things like, oh, if you have a glass that has an opening on top, when you put it upside down, then the liquid will come out, and it's liquid in it to begin with. Stuff like that, you can reason with Psych. But even Psych was very small. It is still fairly small comparable to what happened ever since Wikipedia came along. Wikipedia, with their info boxes, all of a sudden allowed hundreds of thousands of people to formalize knowledge with very little effort. And then, even though Wikipedia was not planning on that, somebody came up with the idea, oh, we should just take that. It's in a structured format, it's a template, let's just extract that. And that's how DBpedia came up, and that's how Yago was born. And basically that's how also Freebase, and whatever Google and Bing are using now, got their initial knowledge. So they have fairly high confidence in those facts because they're human generated, they're human verified, because Wikipedia has a great verification feature, right? It's edited by everybody, and everybody can see, oh, there's an error, and immediately fix it. And these pages tend to converge to correct information. Somebody actually did a study, because initially Wikipedia did not have a very good reputation. So somebody did a study and compared Wikipedia to the Encyclopedia Britannica and found roughly the same error rate in both. So ever since, Wikipedia has gotten a better reputation. So you get verified knowledge from there, you take that to your initial knowledge base, and then Google took this knowledge base, and that's also something I did for my dissertation. Take all the facts I can find on Wikipedia and train machine learning techniques. So, and given that, you can see how well something new that you find fits in there. And you go maybe one step and see how a number of newly extracted entities or relationships fits into what you have, and then in a bootstrapping kind of manner, you go on from there. So, and I don't know about Google's verification procedure and how they do it with their knowledge graph, but I assume they Google is usually very conservative in putting facts on the web. So, you know how Google had limited question answering for a couple of years now, like when you asked where was this person born, when was this person born, it will answer that, but it won't answer all that much, because they want their stuff to be correct when they answer the question. So I assume that also the Google Knowledge Graph has a verification procedure. But Google is somewhat tight-lipped. Can see each other. But I think something that all these things have in common now is a lot of the knowledge that computers are working on these days, at least in this linked data environment, is actually human-created knowledge. It's, a lot of it is not extracted with sophisticated machine learning techniques, but just taking what humans wrote on the web, like what they already formalized on Wikipedia. And then augmented by something. So there was a lot of work, and Wikipedia does not classify it properly. Wikipedia has more of an associative classification system rather than one of true inheritance. So remember that nanotechnology was classified to physics and science fiction. So nanotechnology is not a type of science fiction, right? So it's associative. So some things that work very well automatically is classification of these kinds of categories of media, so to make a more ontology-like structure. And I believe that is what Freebase and the Google Knowledge Graph are doing automatically, and then build on top of that. But a lot is really just human created. There's a lot to do for computer science.
So, Tata, remember you had a little computer semantics, right? So can you explain that part as well?
Yeah. Well, so continuous semantics was an application of
I think you probably lost all the video. Somebody should have reminded.
Can you read? This is the one. Like microphone.
oh.
It's not recorded.
That was an application of automatic model creation. And so one of the features of my dissertation work, one tool is called Dozer. It creates limited domain models based on keyword query. So the example I had in the dissertation and in the presentation I can see is India-Pakistan conflict. So when you query Google for these terms, you get a few relevant pages, but you don't get any factual information, as you would actually by now do when you just Google India or Pakistan. You get a little bit of factual information on the side. So what Dozer then would do is create a model that puts all the concepts that are relevant to this conflict in context. It finds, of course, India and Pakistan. It finds a couple of wars that were fought. It finds the regions that the wars or the conflict is about. It, for example, does not only find Kashmir, but it finds the Indian and the Pakistani parts of Kashmir. So it puts all that nicely together. Now, with a model like that, and if you have a very simple way of creating that, you can then, if it's let's say there's an emergent topic. I think that particular example is fairly stable right now. Let's say in the same manner we have an emergent event the model. The next day, you put in, what was it called, the March of 10,000, March of the Millions, something like that. You put that in, so, and it rebuilds your model with that new information. So you can kind of continuously update this model. We'll maybe throw some old things out, bring some new things in. So you can have semantic representation that is continuously updated. That's behind this term, continuous semantics. And then what we tried was to use this model, this continuously updated model, to filter Twitter streams. And not just filter them, but also analyze the filtered streams to look for new terms, and then update the model. Pavan actually did that. Update the model with the new terms that were filtered from Twitter and somehow analyzed to be important terms in the feed.
So let's say when you have new information come, right? If that information is a conflict or something inconsistent with existing knowledge, so you remove the old one and you keep the new one.
That would require to have representation that allows for conflict detection. RDF by itself, for example, does not do that. So as soon as you have all representation, some sort of first order logic representation that is expressive enough. So we, for example, did not get any restriction information from Wikipedia. You cannot say based on Wikipedia that this class of things is disjoint from another class of things. So any model that is built by analyzing Wikipedia, by just taking categories from there and entities from there, will not be able to do that. Yeah. And that may not be desirable. So when you're filtering news feeds, you may have a lot of conflicting information there. And it's often up to you to decide which one you want to believe in. Yeah. So depending on the application, you don't want to weed out information just because it's difficult to see.
So let's say if you get a tweet, right? So some of them are not fact, let's say opinion.
Oh.
So do you represent them as opinion in contrast with facts in your model?
You need other mechanisms for that. So the filtering would kind of only transform the conceptual model into a set of keywords that then, or into maybe a keyword classifier with weights on it. There could be many ways, but the filtering will still always be done on keywords. Well, in our example, and then you could maybe apply some sentiment analysis work. If a tweet is highly loaded, any sentiment, maybe that's not factual. Things like that. This model-based filtering did not do that.
How do you distinguish between ontology and knowledge base? What's the difference? How do you distinguish between a knowledge base and ontology?
The difference between knowledge base and ontology. Definition. Actually, it's contentious, that question. So there's a paper by Guarino where he tries to give a definition, and even there he doesn't say, okay, this is the correct definition. This is the difference between ontologies and knowledge bases. I think, very often when we say ontology, or many people when they say ontology, they mean the class structure with restrictions on the classes. Whereas the knowledge base is kind of the, are you familiar with the terms A box and T box? So A box, the T box, kind of the axioms of the according to some definition.
Yeah, it's vague, right?
Well, it's like, yeah, the term is held vague because people use it in different ways.
So I have seen in some papers they use populated ontologies to
Right.
say that the ontology is populated with instances.
Exactly, yeah. And we, for example, do that. Ontology should be populated to be useful in the world. So you could say we add a knowledge base, but that is also not correct. When in AI you talk about a knowledge base, that also had rules in it. Yeah, so it's, I suggest read that Guarino papers. It's what's it called? Something with clarification on ontologies and knowledge bases. And Nicola Guarino is one of the early, most cited, most read experts on ontologies and semantic theory. Nicola Guarino.
Could you give an ontology learning?
Hmm?
Ontology learning, could you give ontology learning?
No, not really.
Somehow you did that somehow,
Yeah.
right? But do you think that's a
Well-
area of people can still working on?
Well, I think that can be worked on. I think every paper to date that claims ontology learning did actually something else other than ontology learning.
So what is
Did
ontology learning?
information extraction and did so. So by the definition of what an ontology is, like if you actually go with a strict definition of ontology, like have a completely correct class hierarchy with restrictions in it, proper classification, that's part of the correctness. Ontology learning approaches usually make mistakes. So ontology by definition should be correct. So whatever we have what is incorrect wouldn't necessarily call ontology, or if it's not restricted, if it's not really conceptual. So for example, it is not enough to extract some terms from text and build a hierarchy out of that. Because ontology is the simplest definition of ontology that is always brought up is a specification of a shared conceptualization. Right? So, and what's in there is that you formalize concepts, and concepts can have names, but philosophically, what should be in there are the concepts, not the names of the concepts. So vocabulary has words in it. Thesaurus has words and synonyms. It explains those words. Ontology should elevate that to a conceptual level. And the concept is more than just the word and its synonyms. So if you think of cars, you have an idea what a car is, and you know that there are different terms for it. Many of you have speak different languages. In all of these languages, you have a word for a car, but your idea of what a car is in your mental representation. In English, you have car, you have automobile, things like that. But the ontology should represent the concept of the car, and then you attach the labels to it in all languages that you see fit. So it is very difficult because you need, like, to actually do ontology learning, you would have to tap into the minds of the group that wants to create the ontology. And that's also in that definition, like specification of a shared conceptualization. Like it's a group of people that kind of have a shared idea of how things are. You have a group of biologists who have a certain idea of how things exist in their field.
So does it apply that ontology should always be created manually or at least be verified?
Verified, most definitely, yeah. And
Commitment. Ontology commitment is very important.
Yeah.
People have agreed that you know who are you doing. Knowledge base doesn't be right.
yeah. In, I think you can always like, take some hints from an automatic extraction. Yeah. It's often also easier for people to like, change something or remove something from a body of work that already exists, rather than starting from scratch. If you have nothing and I tell you here, create an ontology on that, you may not initially think of everything that is involved in that field that you should create an ontology of. If I give you some terms, even if it's just terms, right, not concepts, like, oh yeah, now I understand a little more, well this is not part of it, this is not part of it, so let's create a conceptualization out of that. These are synonyms, they both refer to the same concept. That may make it easier for you to, but I think to date there's no automatic procedure to really create an ontology. There's information extraction, which is good, yeah, it's great stuff, but I think it's right now wrong to say that somebody's doing ontology learning.
So how is ontology learning different than ontology enrichment? Because there have been a lot of papers, in fact, published since I think 2002 3 in the areas of just crawling the web. There's one paper which just crawls the web for text and using their own methods of, I don't know, code inhibition and things like that, they are enriching an ontology. That's the word they use. They say that we have this ontology already for a particular domain, like a drug domain, for example, a biomedical domain with drugs and reviews of drugs, the side effects of drugs, so to speak. And then they're crawling the web for text and then enriching this ontology. So how is this different than learning?
Well, one thing that actually makes it easier is that you do have some knowledge already that you can. So usually they would probably extract instances that they classify into
Yes.
things that they already know. So you have a little more certainty on the correctness of things that you extract. But I would still, in those papers, look for validation procedure that they deploy. If they say they're not 100% correct, then I would say it's still ontology. So I would not call DBpedia an ontology either. So DBpedia has some things that an ontology also has, but for example, it does not have this kind of ontological commitment to where to make a cutoff between classes and instances. So because it treats articles on Wikipedia as instances, which is so it's a natural thing to do when you extract this data from Wikipedia. You have an article that's the lowest level in the Wikipedia hierarchy, so you kind of treat that as the instance. So what about the Wikipedia article that talks about cancers? That should be defining a class of things with an explanation that is written in the text. Right? But likely Wikipedia, I don't know for sure, but likely Wikipedia will have an instance called cancers. So you don't have this rigorous modeling that is needed for a proper ontology. But also it's an opinion that you have. Okay? So other people would probably say, yeah, it's perfectly fine to call it ontology learning, ontology enrichment. have not really been told. Because until I start, they don't talk to me really. Even though I signed non-disclosure.
Hello guys, my name is Swapnil and I'm starting the second part of the advanced application in semantic web. So first I want to there's a guy, his name is Tony, and that guy got an idea about he wants to develop some application related with real-time data analysis, like using a using a tweet to make some kind of advanced applications. So he went to a professor and asked about, he wanted to know about the presentation, what all about the idea actually. So he went to the professor and asked about, this is my idea and it's how it's about it. He presented it. Now professor came up with some idea and asked the student, why you're not going to let's talk about the first, what's scalability in the project. So he said oh, what is scalability? So now professor is going to explain about the scalability. So this is our first topic, is one of the subtopic of the first topic is scalability. So what scalability is all about? So what it means, scalability means if your system is able to or capable to deal with large amount of data and say it's able to perform some computations syntactically and interpretation of the data. If your system is able to do this, then your system is scalable, right? I am talking about the data. So what is the data is? I am talking about the real-time data analysis. So if your system is able to do a real-time analysis on data with performing some computations and with performing some interpretation on data, then your system is much capable to scalable to do something. Your system is much scalable. So as I talked about two things about scalability. First is computation or syntactical analysis, right? And second I talked about the semantically, right? That is all about interpretation on data. So as we discussed, we have two types of scalability. First is syntactic computation scalability and the semantic scalability. When we talk about the scalability, syntactic scalability, what it's all about? Like extracting a data, performing some kind of you can say searching, like extracting a data and do some kind of not analysis, just little bit syntactically perform. So if these kinds of data is there, so how you achieve the scalability in the syntactic computation? Just only you have to increase your platform, you have to use your cloud. You can increase your you can say your server processing power. So you can increase and decrease according to the type of data. So you can achieve a syntactic computation scalability by increase your resources. Now second part is semantic analysis. As I mentioned about, if your system is scalable, then your system is performing computation and performing some interpretation on data, right? So interpretation on data means you are doing some kind of semantic analysis, right? So semantic analysis, if you are doing some kind of semantic analysis, so then so there's actually in semantic analysis there are some keywords like spatial, temporal, and thematic comes. So in our topic, in the first topic, they are talk about how we are going to use the spatial, temporal, and thematic to achieve a semantic scalability. So first I talk about what this term is all about. As we discussed, spatial means where or place, right?
and temporal means time, and thematic means event, right? So I think there's a one example in which is developed into. Again, here Tony comes and he asks like, Professor, can you explain, given us some example about this spatial temporal thematic which application is already developed. Now the professor gave an example of Tutris. Tutris is developed in Oasis Center. So the Tutris, what it does, it extracts the event using the some kind of event or theme, right? Like suppose an example of US election, and US election will extract the data from the tweet according to the theme, and that is called filtering the data according to the theme, right? And then using the temporal or spatial to slice the data, right? So here what it does, like take an example of US election. US election is a theme, and then now how the people are talking about the US election in Ohio State and on a particular date, and then the next day how the people talking about the US election in Florida. So like Florida and Ohio, these are the spatial, like your place, and the time is on which, suppose the 1st November 2012 and the 2nd November of 2012 in Florida. So like this is an example of spatial temporal theme.
What is the scalability there?
Yeah, I come.
Okay.
So this is an example of to this also, like the first part is data collection and second part is data processing. Like your data collection is part like you're extracting a keyword theme using some keyword and going to look up some locations and the time also. Here you are processing on these data actually, spatial, temporal and thematic description, and performing some kind of analysis on this. So this is a description again that we all talk about. So this is again a screenshot of Tutris where US election talking about on 7th of October in Ohio State, what the people are talking about, and in Ohio State, in Florida, in Iowa, what the people are talking about, it's a different time, and about the US election. So here the US election is a theme, and the time is your like date, and a different places means your spatial election. So as we saw the first part of how semantic like works, spatial temporal and thematic how works in the part of Tutris. The second example, one of the professor, Dr. Seth gave one of his presentation. He talked about how semantic web through space, time, and theme. Okay, so there is another example in which what happened if you have a suppose there's a example of, suppose there's a football play, right? So that football play is like your theme, right? There are various sensors, like the one sensor is like which recording the video. The second sensor is talking about is capturing the commentary at the same time, and third sensor like your image sensor which capturing the image, right? So what kinds of application you can develop with using these different sensors collecting different data at the same time about the same particular theme. So you can develop such kind of application where you can what you can do, you can take the data from which captured by the video, then you can take the commentary which is captured by some other sensor using the temporal, the time of each frame and the commentary, you can merge them and you come up with combined application where you showing your video as well as commentary at the same time. And simultaneously, whatever the whatever the image you have captured, right? So you can give different view of the same place via at the different time, right, or the same time. So this is another example of spatial, time, and temporal. So this is architecture of the application which I discussed just now. Is an example. We need a event web infrastructure for that. So this is like it's divided into 3 layers. The first is catalog service. Second layer is like your all the services are there, and third is event registry. So what happened in catalog services? Like it has all services which contains all the service name which can discovered by the users, and the second are the services which helps to the user to access that data, and the third is event registry which is useful for registering the event or updating the event here. User can update the event using the update event service to the event registry application. So using this kind of architecture, you can develop your applications. So this is third, as I discussed, 2 aspects of semantic, spatial, temporal, or thematic applications. And the third which I got from the internet actually, maybe how it is useful.
He's not searching for that.
How semantic scalability can help to scale a video as well. You can see here.
Refresh the page.
Try clicking the link on the title bar of the video. If it's down on the video, it'll take you to the YouTube page. Go down more.
Another aspect of semantic scalability through scaling the video as well. Let's read the text. The first part explain like if you reduce your bit rate, so how it's gonna affect your screen resolution. Okay, but if you are using semantic scalability, so how it helps even like without scaling your video. Temporal domain that they're talking about. and what it's happening here, like, so what they are doing, like they are scaling the they are understanding the semantic of particular video or domain, and they are scaling their video according to that. Like if they the space, like they are using the same background again for displaying at the time of non-play, right? So this is kind of example of semantic, spatial, or temporal, or thematic scalability. So semantic scalability, using these all three parts.
Is that the only kind where you don't transmit background info, you're just transmitting foreground information? Because that won't be applicable to a lot of other types of videos, right?
Yes, it's, but here what happened, like you have to understand the semantic of that particular domain. Like here the games are there, so they know about the semantic of that particular domain, means your tennis. So according to that, they are scaling the video. So if it is other domain, so you have to understand that semantic and then scale the video according to that. So that is different part. So as we discuss about so here the second part. What happened, like the Tony understood. So Tony understood what is all about scalability. Now Professor said, like why don't you work on the continuous semantic as well? So he thought, like what is all about this continuous semantic? He said, like you have an ontology in there, right? And you have to update ontology according to the data. So now the professor is explaining what is all about the continuous semantic, right? So before continuous semantic, I just want to tell you, like whatever semantic application or advanced application is there, you have an ontology, right? The ontology is developed by the expert group, and they update the ontology according to whenever the new facts comes, right? Or whenever the facts changes, they update the ontology, right? And it does not happen very frequently. It takes time, like whenever the new fact comes, right? But that depends on the data actually. If your domain is such like where the data does not change very frequently, so you don't need to update your ontology very frequently. But there are certain kinds of data where the data is comes in a very like your streams of data, like the floods of data comes, and the new facts, new semantics comes, right, in that particular data. So you have to update the ontology according to that. So the continuous semantic is what all about, like when you have a certain kinds of data, that data will comes with large amount of data, and it's the data which has so many semantic in that, right? So you have to update your ontology according to that semantic data, semantic. Okay. So as I discuss about what's the characteristic of the data. Data is very spontaneous, or it's a real time or near real time data. And the third is all about, like it's a very different viewpoint on the particular data, right? The same data. So if these kinds of data you have a large amount of volumes of data, then you will get lot of semantic in that. So your new facts or the fact will changes very frequently. So according to that, you have to update your ontology. So, but before updating the ontology, you have to verify that whatever the semantic you have found is valid or not, right? So you have to verify from a particular source. That authenticate source could be a Wikipedia, right? Wikipedia. So here, like to build a domain model of this situation, here this explanation. We must pull background knowledge from trusted and controversial source Wikipedia, for instance. Like as I mentioned, whatever the new semantic you have got, you have to verify first whether the semantic you have is valid or not. So you have to authorize it first. It just so as an example, Wikipedia is there. Then you can update your ontology according to that. So this is one of the paper presented by Dr. Seth also, is a diagram where the like is a web of thing, web of circle, sorry. So in this what happened, the explanation here, like the circle of knowledge life on the web. So the first part it says discourse and analysis, background knowledge and information knowledge extraction. So what happened, like as I mentioned earlier, you will extract the information from large amount of data. You find the semantic in there. You verify the semantic from the particular source, and then you update your ontology. So we recently talked about the Dozer as well. The Dozer application does the semantically like they are doing same thing here. What happened, like you have a entity, right? So entity, you get the entity from the particular data. Once you get the entity, you find the relationship, what the relationship between the entities. So you extract the Dozer the same thing. You provide the entity, it will extract the relationship between the entity and give you the result. So that result is as a model. So here the example. It is developed in Oasis. Suppose these are the entities which you have given, and you submit this entity. It will extract the relationship between these entities from Wikipedia. And give you the data in RDF form. This is your data, which is in RDF form, which contains the relationship between the entities. So, what is exposed session? So it gives you the RDF form actually. So I will come up with one more diagram here.
Result, like what is the relationship between, right?
So here, like even recently we were talking about like how Dozer will help to get the semantic of and between the entities. So like in a Twitterist we get the data, we extract the entity here, we get the data here, we extract the entity from here, and we will come some entities, right? These are the president, Iranian election, Iran. When we give this entity to the Dozer, Dozer will extract all kinds of relationship between these entity and give you the result as a RDF form, right? You can use this relationship or model to come up with the new entity to help the data extraction. So this is a all cycle which you can use for continuous semantic. This is called continuous semantic, where you extract the entity and come up with the relationship, and then again you use the relationship to define your most search in the Twitter. It's the same which I described here. This is the same thing is written. This is a RDF diagram which contains the relationship between the entities, which given by the Dozer. And the description here actually. Now third part comes like Internet of Things. What's Internet of Things? Means like in the real world there are many physical objects, like even human beings, resources, devices, and lot of and sensors, right? These are all devices. If they are connected to the internet, right, and they are putting their data to the internet, then Internet of Things comes, right? So they are connected with the internet, and using once they are connected to the internet, they share the information, right? So that is called Internet of Thing. So what kinds of devices can be connected? Like could be anything, right? And one example of Internet of Things, like suppose there is a sensor. One sensor is your mobile, right? And another sensor which air traffic in traffic, where analyze the traffic, right? So if your sensor gives some kind of data to the driver, right, that if you go to particular location after this time, you will get a lot of traffic, right? So it means what happening? Your mobile, your sensor, they are connecting to each other. They are sharing the information to each other. So they are helping the users to understand or take the intelligent decision, right? So this is one of the primary goal of Internet of Things. Right? So there's a one fact all about how during 2008 the number of things connected to the internet exceeded the number of people on earth, or in by 2020 like 15 billion things will be connected to the internet, more than human beings. So the primary goal, as I discussed about it, the primary goal of interactive device means once they are connected to the internet, when they share the information between to each other, they perform some kind of analysis and resolve some kind of query, right? For to whom? To aware the environmental situation. So as I discussed, like when you have a traffic, right, and so they are understanding the environment situation, or making the situation awareness kind of enable application. The application which I discussed is a situation awareness application. So the understanding of situation and context between. Okay. So it helps the human being to make the intelligent decisions, right? So the one of the primary goal for the Internet of Things. So what are the challenges in IoT? As you know, that number of devices are there, right? So the devices, are very heterogeneous devices, you can say, right? You need a interoperability between these devices, right? How they can handle the large amount of data, right? So these are the challenges between for IoT, right? So even Semantic Web come up with one solution for this heterogeneity. They have some kind of framework which are called Open Geospatial Consortium, where it helps to connect multiple or heterogeneous devices and provide interoperability between them. So this is semantic technology for IoT. This is one last slide which contain which tell about things-oriented vision, internet-oriented vision, and semantic-oriented. So IoT comes here. Actually, it contains all these three things.
That was interesting, actually. It's trying to actually see the intersection between.
Yeah, between the semantic oriented vision and inter-oriented vision, and the things oriented vision.
Well, it's not necessary that everybody thinks of semantics as a necessary component of Internet of Things. So I think in the mind of many people, Internet of Things will remain viable with or without a semantic web. So I don't think we should have a semantics oriented vision to be a necessary requirement of this. I think what you might call is a semantic empowered Internet of Things, the part that is of our book. That, yes, is an intersection, but IoT itself doesn't need to have semantics aspect of it. It does require devices, it requires internet access.
But if their devices are connected to each other, or to the internet, so what the purpose for them? If they need a
Or just access to
semantic
data, for
web.
example. So suppose there is this a device called environment egg. It tells you about carbon dioxide and nitrogen oxide and that kind of thing, or how much particulate matter there is in the air. And you can buy this and put anywhere, all around the country. There are people who have bought that. All that data get reported, and then you can see on the Google mashup, in mashup, data from everywhere else. Well, there's no need for semantics if you are trying to simply get data, access to the data. What is current, level of this particulate matter in this location if there happens to be this particular sensor. So there again, semantics is not necessary. All you're getting is data, access to data. Then semantics is not necessary, right? So just Internet of Things itself by itself does not imply any use of semantics. What we are focusing on in our this book and this course is, if you have semantics, like you have noted all the data coming from IoT, then it is very easy for you to semantic integration of the data, to create a semantic mashup of the data, to do query across multiple data sets, or to convert that data into, ask questions like, tell me the places which have smog right now, where smog is defined as a combination of multiple factors. Now that would have to be computed, and there is a definition of smog, a semantic description of smog, translated into rules or a bunch of values coming from multiple sensors that need to be integrated. In that particular context, you are trying to, there the role of semantics would be clear. And that would be an example of semantics empowered IoT. I think that is a decision.
Did you come up with that video by yourself?
No,
or did you
I gave a reference here. That is one of the presentation given by the Corey actually. That,
Corey?
yeah.
Corey Hansen?
So that images I call it.
Good. I think it's a good job. Really good job. Okay. Any questions? All right. I want to make sure now, Mary's thing, you inserted your stuff. Okay. Everybody has. Who has not done 3 reviews? Okay. Other than Alan, anybody else? Everybody else has done 3 reviews. Other than Alan's, I think own submission. Everything else should have 3 reviews also, right?
And also submission 0F6 is also.
Okay, I'll have to see who that happens. 0F6 is missing? Yeah. So we'll try to get that in.
There were a lot of problems with that document that had the reviews in it. I read through the whole thing. There were a lot of submissions missing from it.
Really?
Yeah.
Well, I asked everybody to check.
And then a lot of them were duplicated as well. Some of the reviews I think were duplicated in different parts of the paper. Unless they were actually copied and pasted and submitted as separate reviews. I'm not sure. But
Yeah, it was a nightmare. There were a lot of emails and you cut and paste, and there were also, I don't know whether some problems occur when Google Doc becomes too large. Why don't everybody check that your submission is right and that your review is where it should be, right? And send me an email at my Gmail account, okay? And I might as well copy to my noesis.org account also, just to be sure. And do it today. We'll, I guess, so on in the next class, then we'll be reviewing assignment, okay? The reviews and stuff.
Dr. Chef, after this presentation, I was the only one who did not present.
Right,
What
so
is
we,
that topic?
we have to think about it. You are always a special case. Okay, yeah, I'm aware of it.
Can I talk about my research?
No.
Related to the semantics?
We'll see. No, everybody has done extra work beyond their research, so you also do it. Okay. And I hope the project work is going on well.